Okay, perfect. Start recording. Okay, so free body diagrams are really useful. I'm going to go through all the different things you need to know. Some of them we've done before, especially vector, magnitude, weight, and resultant force. But what is a free body diagram? This is really important. It's a really simplified drawing, and you use arrows to show all the force acting on a single isolated object. It's just the object you're looking at. We looked at resultant force, the overall single force on an object, and you work it out by combining all the individual forces. A vector, both magnitude, which is how big it is, the size, the numerical value, and the direction. And I'm just going to add to this. With a vector, with an arrow, the arrow tells you the direction, the length of the arrow tells you the size. The longer the arrow, the greater, in this case, what we're looking at is forces, so the greater the force. Magnitude is the size of the force. As I said, use the length of the arrow, or simply the number, 3 newtons. All right, that is the size of it. Weight is the downward force, and I like the word downward is something I'm not too keen on. Pulling you down to the center of the earth. You're being pulled towards the center. We look very briefly at the normal contact force. It is the upward force exerted by a surface that supports the weight of an object. Usually it's just sat on it. And I'm assuming you're all familiar with air resistance. It pushes you in the opposite direction to the motion, in which direction you're going in. All right. So the reason I really like free body diagrams is we use really simple drawings. So when someone says a car, I draw a square. That's a rectangle. So we'll stick to a rectangle, shall we? And even that, sometimes I just don't bother and I think, right, I'm looking at a car or I just might a circle. Or even a simple dot will do. Right? It's fast and you're just not trying to draw a diagram of a dot of a car or something. So the object that you're looking at, whether it's a person, a car, a bike, just draw a square or a circle or a dot. Right. Force arrows must start from the center of the object and point away from it. The center of the object. And we looked at center of mass and things. The length of the arrow represents the magnitude, how the size of the force. So the longer the arrow, the bigger the force. Direction I pointed, this simple. Whichever way the arrow's pointing, that tells you the direction of your vector. Equilibrium. If your resultant force is zero, now here's a really common thing. Everyone thinks it's stationary. It's not. It's moving at a constant velocity. What's really cool is if you really get into physics, there's no such thing as a stationary object. There's nothing that is not moving. But that's for a different time. Okie dokie. Newton's second law. F equals ma. Oh, that didn't come out very right. Yeah, very nicely. F equals ma. If you have a resultant force, right, your object will accelerate. What do I mean by accelerate? It will change speed. Either it will speed up or slow down. Okie dokie. So I grabbed a couple of images just to talk to you about certain things. All right. Now, certain forces. When you hang a picture up, there is tension. You know that. There's tension in this string, and we point that upwards. All right. It's as if the string is stopping it falling down. And if I think about it, it's really interesting. I've got its weight from the center down. This big arrow coming down must be equal to these two little arrows when you stick them together. Right? Otherwise, the object would either be falling down or moving upwards. And the way that I would draw this is, whatever shape, I'm going to draw a dot. And the weight is down. There's my free body diagram. Now, it becomes really awkward when you try drawing this because they've got to be linked together. That really doesn't work. So whether their angles, as long as the angles are the same, the direction doesn't matter. And it's like, all right, fine. One is pulling it that way and one is pulling it that way. All right. And there's a free body diagram of the forces on this picture. All right. Now, the normal contact force is always 90 degrees. And we did that as well, to whichever plane it's sat on. Upthrust, that's the force of which the water is pushing the boat upwards, and we call it upthrust. Right, so let's have a look at a few diagrams. Air resistance, this is a parachute. The air resistance is applying a force upwards, and this person's weight is a force downwards. And they're not picking up speed, they're falling at a gentle speed. All right, let's pick another one. Oh, that was that diagram I showed you, weight and tension. So I want to show you a really complicated one. And this is really common. Now, left and right are completely separate to up and down. Right? We call them component forces. They've got nothing to do with each other. So what I'm going to talk about is up and down first. This car is not flying or sinking into the road. So its overall resultant force up and down is zero. It has to be, or else it's flying or sinking. Its weight is downwards. And the normal force, the reaction force, is exactly the same size and upwards. Okay. Now, if this car is cruising along, let's say 30 miles per hour, we're not going to say miles per hour, we're going to say meters per second, because that's the units we always use for velocity, and we know this is velocity. Now, the thrust of the engine drags it forward, it pushes it forward, and friction on the tyres slow it down. It's almost like there's a little gremlin holding onto the car and going, right, come on, I'm going to pull you backwards. These two have to be the same size for the car to remain at 30 meters per second. But when you look at the diagram, obvious here that the thrust to the right is bigger. I don't really need to know how much bigger, but I know it's bigger. All right. So what I'm going to do is one way I picture in my head is if I draw that blue arrow, and I think, right, okay, yeah, fine. There's blue arrow to my right. I know that brown arrow's smaller. I'm not really concerned about how much smaller. I just kind of overlap it. And what I'm really saying is I'm going to take my thrust and minus my friction. And these two aren't the same size. So you're going to have a resultant force to the right. So this car is not going to change at stay at 30 meters per second. Its velocity is going to increase. It's going to increase to the right. Okay, these are free body diagrams. They're really, really helpful. All right, so you got some really nice. I've tried to make these questions as easy as possible, right, to start with, and then they get really tough. Your job is to actually, when you're answering a question, to do a free body diagram. Most students don't. It's exactly like when I say underline your keywords and put a box around your command words. Not many students do.